Hi there and welcome to this video for Senior Physics where we're looking at nuclear physics. In this video we're going to be looking at the different types of decay and how they relate to equations. Once we've put the equations together, we'll then pull the information that we've got to produce a graph and look at how we'll know whether something is stable or unstable, and as a result what particles are going to be released. Now we already know that we've got three main types of radioactive decay. We've got alpha, we've got beta, and we've got gamma. So we're now going to pull those together and look at how they're affected or how they're utilized within the equation. So the first one we're going to look at is alpha decay. Now alpha decay often occurs due to man-made isotopes which are too heavy. So once they're made in the laboratory, they are there's a huge instability, and as a result they spit out the alpha decay. In nature this is less likely to happen, not always, but it's less likely to happen. Now remember that a alpha decay is basically a helium nucleus, and a helium nucleus is made up of 2 protons and 2 neutrons. Remember, we're talking about the nucleus and not the atom, so we can ignore the electrons. Once those have been emitted, there is then high energy which is going to be generated in the form of gamma. So let's look at this in the form of an equation. So here I've got Pa236 is going to break down to AC232. It's going to emit an alpha particle or a helium nucleus, and we're also going to get some excess energy in the form of gamma. Note from our previous video that on the right hand side, if I add the masses, which are on the top there, 232 plus 4 makes 236, that equals what's on the left hand side, and 89 plus 2 makes 91, that also equals what's on the left hand side. So what I've got is I've got my mass and my atomic number all balance. So where does the excess energy come from? Well, from our first post on this course, we looked at mass defect. There's obviously an imbalance in mass. There's going to be more mass on the left hand side than there is on the right hand side. So where has that mass deficit come from, or how is it released? Comes off in the form of energy. Remember, all mass and hence all energy must be conserved. So that's the alpha decay. So let's look at beta decay. Well, beta decay, as we know, is the electron. And we know that the electron is generated from the breakdown of a neutron. A neutron can break down into a proton and an electron. But also we get something called a positron. Now we're not going to go into this in any great detail, but a positron is identical to an electron, except it's the opposite side. It's an opposite charge. It has the same mass, it's just got an opposite charge. And these are basically, if they were to come together with the electron and the positron, they would annihilate each other because they're the opposites of the same thing. So they're basically termed, or positron is basically termed as antimatter. So how do we use this when we put this into an equation? Well, if we've got too many neutrons, what happens is they will break down and they will be released in the form of an electron. Now the key thing to understand about the right hand side here is that if I was to add 93 and -1, I'd end up with 92. We have to use the algorithm, which you can see at the end of the last sentence there. 92 minus -1 equals 93, or 93 minus 1 will equal 92. So we can go from the right hand side to the left, or if I know that uranium-239 basically releases an electron, then I can take 92, and I've got to take 92 minus -1. A minus and a minus makes a plus, so they can add them together. So as a result, I can go from one side to the other. The real problem that I found with students is that they forget that it's a -1. So if you add together the right hand side, you'll get 93 plus -1, that equals 92, that's easy. But if you want to find what MP is, it would be 92 minus -1, so we have to combine them together to make a plus, and that's where the 93 comes from. And if you think about what's happening in the uranium there, one of the neutrons is breaking down. So it breaks down and it emits the electron, but what's left over is another proton. So hence that's why we've gone from 92 to 93. So I hope that makes sense. Now, if we've got too few too many protons, then what happens is we then get a particle which is emitted in the form of a positron, and then we can use this as normal. So we get the same sort of process which is occurring here. This is the breakdown of a proton to produce a neutron and an electron, or positron in this case. So we've now got the proton which is breaking down. Now the rules with respect to the equation are the same as normal. So as a result, if I had MP239 and I was emitting a positron, how do I work out what's left over? Well, I just take 93 minus plus 1, and that gives me 92. And likewise, if I wanted to work out what is the starting atom, I do uranium-239, which is 92, plus positive 1, add them together, and I get 93. So it's fairly straightforward. As I stated earlier, electrons and positrons are antiparticles, and when they meet, they can't occupy the same space, they explode, and the mass is converted into energy. So I hope that makes sense in that respect. The last form of decay is obviously gamma, and gamma just comes off as electromagnetic radiation. There is no change to the mass or the atomic number, but we have to add that on the end of the equation, because obviously we want to show that mass is conserved all the way through, and hence mass is energy. So that means that we've got a complete equation which is going to be generated. And often what we need to do is to produce the equation, then use the calculations to work out, well, how much energy is going to be created. So we can put all this onto a graph. Now here I've got a graph of the number of protons versus the number of neutrons. Now remember, we talked about neutron to proton stability or ratio, and if they're on 1, then they're going to be stable. So if it's a 1-to-1 neutron to proton, the particles are going to be stable. However, if we get to an imbalance either on the neutron side or the proton side, then the result is we're going to get a different type of decay. So you can see here that the dots which are on the graph are going to represent our stable nuclei, and you can see that shown with the blue line. Basically, where they're together, we've got a 1-to-1 relationship between neutrons and protons. So that's what the blue line is basically stating. However, if we move and have too many protons, then what will happen is we will emit positrons. Remember, the protons will break down to produce a neutron and a positron. The positron will then be emitted. And likewise, if we have too many neutrons, will emit electrons. So the neutron will actually break down to produce a proton and an electron, so they will be emitted. So we've got beta decay via positrons, beta decay by electrons, depending on this imbalance between too many neutrons or too many protons. And that's how the graph basically can be utilized. Okay, well, I hope that sort of makes some sense with respect to the types of decay and how we can incorporate them into a nuclear equation. So I look forward to you meeting me again, and bye for now.